Hello, everyone. Thanks for joining. My name is Works. I'm a software architect and the DevOps lead at OwnID for the past year and a half, almost 2 years. I'm here to talk with you today about the journey of crafting and validating our disaster recovery plan at OwnID. Before we start, I have a question. Does anyone recognize these dates? Who can guess what's common to all of them? Well, these are outage dates of US East 1 AWS region for the past 2 years. Once in a while, a critical service is down, and then many dependent services goes down with it. So let me tell you something, you have the power to design your architecture to be resilient and not being one of these unavailable services that goes down when everyone does, okay? So this is the definition of resiliency-enabled AWS docs. The ability for a system to recover from a failure induced by load, attacks, and failures. One of the best indications of having resilient architecture is the fact that you have a bombastic DRP, a disaster recovery plan. A few words about myself. At OwnID, I'm leading the infrastructure domain and the backend domain. I'm designing and implementing new features, dealing with observability, performance, production health, etc. Before my current role, I was a tech lead at WalkMe and a commander in the IDF Army Intelligence. I'm a certified AWS solution architect, and I'm holding philosophy BA and MA degrees. What to expect from this session? I will open with a short introduction of a few common concepts and terms you should be familiar with to talk about DRPs. Most of the session will be around the real use case of a DRP architecture, which I designed, implemented, and validated. We will touch many aspects, starting from the high-level architecture and diving into GitHub actions and info as code, tunings, data replication, challenges, and some critical decisions during the process. At the end, I will summarize the main takeaways. So to give you the context of the technical aspect of this session, let's cover shortly our product and where it meets our customers. OwnID provides a seamless web-based authentication solution that eliminates passwords. We are using FIDO2 Webauthn API, also known as passkeys, and a few more technologies. We are a small startup, less than 10 developers. Among our customers, you can find huge enterprise and well-known brands. Millions of end users need our product to work in order to authenticate. What is a DR? First, you have the disaster. In our case, we ask to deal with our production region outage. The suggested recovery is a multi-region architecture. Every disaster should be handled differently, okay? A recovery process that will help you when your production region is not available probably won't help you if someone has taken over your AWS account. So before you start, remember to ask yourself, what is the disaster I'm willing to deal with, and what is my suggested recovery? A DR is a game of ROI. You can spend your whole year building a DR and you cannot do it at all, okay? Before starting to design the DR, you must define what is the availability level that is required from your system during a disaster. Not every component in your organization has the same SLA, so before diving into the technical part, remember to have a well-defined product availability requirements. Business, product, DevOps, all the relevant people need to sit together and discuss. If the cloud cost and the developer working hours that are required to develop and maintain the solution worth it, then you should go for it. Now, we know the business needs. The challenge is to translate all these requirements to a practical DRP architecture. Exactly for this, there are some basic terms that everyone who designs a DRP must know. First, we have the RPO and the RTO. RPO is recovery point objective, and RTO is recovery time objective. The RPO refers to how back will you take me in time once the system is live again. How much data will I lose? RTO refers to how long until the system is active again. A lower RPO and RTO values reduce downtime and data loss, but come at a higher cost and operational complexity. if we focus on our use case at OwnID, our required RPO is 10 seconds. We are storing customers' configurations in our database. For example, the widget color, the OTP configuration, if it will be by email or by SMS. End users' data is not stored on our side, as we don't store real-time data, so we are okay with taking the risk of losing 10 seconds of data. Our data is not tend to change so much, okay? And regarding the RTO, our customers are expecting our product to be 3 nines available. It means that we have a very few minutes of allowed downtime during a month. Once a disaster happens, we need to be live again in not more than 10 minutes. So this is our RTO. After we understand our required RTO and RPO, let's talk about common DRP architectures. The first choice you should make is between active-active and active-passive. In active-active, you have two environments, the operational and the DR. They are running in parallel all the time, okay? They are providing RTO and RPO values that are close to 0. Theoretically, it can be even 0. Active-active is actually the most expensive architecture you can choose. It may double your cloud cost, okay? Netflix, if we take them as an example, they're using active-active-active architecture. So if you are a small startup, your system will survive the disaster amazingly, but not sure that your bank account will survive it. So you need to have it in mind. In active-passive, the DR quality is downgraded in terms of RTO and RPO, but things are getting more realistic, okay? Active-passive is a very flexible approach. The more cost you save, the more required actions you need to perform to bring your DR environment to be fully operational when needed. This affects directly your RTO and RPO. Backup and restore is the minimal DRP you may have. Just backup your data once every few minutes, hours, or days. You can take the decision without any extra preparations. If you have a disaster, you will have to start building your environments from scratch using your data backup. In our case at OwnID, it may take 2 days to create a running environment from scratch. 2 days as RTO are way too much for our requirement, which is 10 minutes. So this approach is not relevant for us. Pilot light and warm standby are the interesting strategies. The main difference between the strategies is the time it takes you to bring your DR environment to be ready for receiving requests. In both strategies, a functional stack is deployed, but with a reduced capacity for cost saving. In warm standby, the DR environment is ready to handle requests without extra manual actions, and in pilot light, extra steps are required. In our case at OwnID, the solution we chose is very close to warm standby, but since we have a few manual steps for the environment to be fully available, it's not a pure warm standby. So I would tag our solution as a pilot light, really close to warm standby, but not there yet. The sweet spot we found between pilot light and warm standby was an output of our RTO and RPO. I just asked myself, does this set of manual actions that I need to do in a disaster will take more than 10 minutes? The RTO is the 10 minutes limit that I have. Since the answer was no, we decided that we are okay with the pilot light approach. So that's all about DRP architectural strategies. When starting to dive into the implementation, first I decided to filter out background noises, services and cloud components that we don't need them to be part of the DRP. I mean, if you have 100 microservices, you need to ask yourself, does all of them need to be fully available during a disaster? You need to translate the ROI, the business decisions, into technical decisions. If, for example, you have a nice-to-have feature in your system, a BI screen that shows to the customer interesting insights about his application, so you decide to leave it out of scope. In the disaster, you need to make sure to leave out of scope also all the microservices that are related. If, for example, it has an Elasticsearch infrastructure with terabytes of data, just have in mind to not include it in your disaster recovery. This is the high-level architecture of the components I'm going to cover. I left some components out of scope just for this session. Let's start from the right of the diagram. End user performs request from the browser to the relevant domain on Route 53, the AWS DNS service. Route 53 is referencing a CloudFront distribution, the AWS CDN service, that its origin is one of both. It can be S3 buckets or static files, or API gateway and load balancers for dynamic server requests. Our Kubernetes cluster, also known as EKS, is communicating with PostgreSDB, Redis, and Secrets Manager AWS service. Once you know what needs to be part of the DRP, the next steps I took is to define the regional and non-regional dependencies. CloudFront, Route 53, and IAM are the only services that are global, which means I can take into account that they will keep functioning even if our primary region is down. AWS handles their resilience behind the scenes for me. Now we can also map the components that won't be available if the region goes down. S3 buckets, Redis, Postgres, Kubernetes, API gateway, and Secrets Manager. Now that we have an overview of the main challenges, we can tackle them one by one. Step one, I want to deal with the data. The stateful part of the system, the data domain, most of the time will be the most complex part to handle under a disaster. We have 4 services that actually have data: Postgres database, Redis, Secrets Manager, and the S3 buckets. First, the RDS, the Postgres database. This is the source of truth of our customer configurations. To promise the backup of the data on another region when needed, we configured a read replica on the DR region. That read replica is updated asynchronously after each write to the primary replica. The read replica lag may be from few milliseconds to few seconds, so it fixes our RPO requirement of 10 seconds. In case that the main region is unavailable, we promote the read replica to be the primary replica, and actually it becomes the main database. Starting from that moment, the read replica, which is now the primary replica, becomes writable, and the previous primary replica is out of the picture. Similar approach was taken with the Secrets Manager by creating secrets replication. As I said, we use S3 buckets to store static content such as web app, code, and translations. We decided that for each bucket, we will have the same equivalent bucket in the DR region. As part of the CD process, we upload the content to the primary bucket and to its equivalent backup bucket. We could use CRR, the cross-region replication, but since the data isn't frequently changed, but only on deployments, we didn't want to create an overhead, and we prefer to keep it simple by performing that backup manually from the CD process. Regarding Redis, the data we store on Redis can be split into 2 main types: the end-user sessions and customer configuration cache. So we decided that there's no need to back up that data to create a replication in another region. To simplify the DRP, we are okay with losing Redis data on a disaster, okay? Let me take you back to the ROI concept that I mentioned before. End user sessions are very temporary, so we are okay with losing them. We are okay with losing a few of them when there's a disaster. The end user experience is broken anyway. So the end user left the authentication process. It won't help if I will wait like 10 minutes and then he will be able to continue with this process. He left a long time ago. And the customer's configuration cache, we are okay with losing it too, because it can be loaded as a fallback from the Postgres database in less than 1 second to all the applications, okay? So we are done with the data components. Now, let's go back to the global services and their resiliency that I talked about before. As you remember, Route 53, CloudFront CDN, and IAM are global services. Although AWS promises high resilience in for these global services, on the disaster, AWS mentions in the documentation that even these services may have a downgraded functionality. AWS services relies on the concept of control plane and data plane. Global services have a dependency on these two components as well. Control plane is responsible for admin API action, such as creating or removing a server. Data plane is responsible for simple common actions, for example, reading data from an S3 bucket. Data plane actions are less complicated and are much highly available than control plane actions. This is why you should avoid from control plane actions on your global components during your recovery process. The decision we took is creating a duplication of all our components in the DR region, except for Route 53 records. Although CloudFront is a global service, switching the origin during a disaster is an action that relies on AWS control plane, so it may not work. So an additional CloudFront distribution for each one of the distributions, pre-configured to the DR region, that's the solution to be on the safe side, doubling everything. Provisioning the resource before the disaster is the right choice. Prevent dependencies on control plane actions. The same approach we also took with the IAM for configuring users, roles, and permissions in advance. Route 53 is configured with the health check and the DNS failover. This is our only consistent component. On a disaster, it will switch automatically the traffic between the CloudFront distributions. The only extra action which is required to complete the DRP is promoting the database read replica to be writable, and then also increase the resources to handle the load of our production environment. So we have the architecture ready. Now things are getting dirty, it hangs on time, someone needs to implement all this beauty, right? So as maybe I mentioned before, maybe I don't remember, but we are managing our infrastructure with Terraform. The DR environment needs to be created using Terraform 2. And to do so, I split our Terraform resources into 3 types. The first type is identical components that need to be duplicated in the DR environment as is. For example, Kubernetes cluster, API gateway, S3 buckets. We need identical copies in both environments. Second type is components that need to be created with a different configuration. For example, database and secrets. We need in one environment a regular database, in second environment, a replica, a read replica of the same database. The third type is components that are reused in both environments that don't need to be created at all on the DR environment. For example, Route 53 records. Since we really don't have time to dive into the details of what I did, I'm going to cover the database module only to give you the idea of my approach. So the challenge was to run the same module for a regular environment that should have a standalone regular database, and for the DR environment that needs to hold a replication of an existing database from another region. I use the flag isDREnv. So for a regular environment, the standalone database is created. You can see the resource. And for the DR environment, a replication for a provided database ARN is created. Everything is based on the flag. On GitHub Actions, I had to make sure that both environments are deployed on a regular basis in parallel jobs, and that there's no region coupling during the process. You can see a different containers registry URL configured for each environment. Just have in mind that all these examples and some more examples are available in the GitHub repository. so you can later dive into them on your free time, okay? After everything is ready, we need to make sure that everything is well documented in an execution plan document. Personally, I wrote it during the first test execution. I performed an action and documented it right away. That's how I created a very nice document that I know which is reliable and really tells you what to do, and it really works. The disaster we are preparing to deal with is a full region outage, but sometimes only a small part of the region may have issues, and it's not sure that you need to perform all your DRP, okay? Small disasters may happen. A single availability zone can have electricity issues, data replication may stop, and so on. If you prepare your system to be resilient for these edge cases, the chances you will have to apply the DRP are smaller, okay? You can use two amazing tools in case you are running your workloads on AWS, and there are equivalent tools on other cloud providers. The first tool is AWS Resilience Hub. That's a tool that scans your entire infrastructure and then it scores your resilience level for each component. An output, for example, may be your RDS X isn't configured as multi-AZ. Okay, it's really nice and helpful insights. The second tool is AWS Fault Injection Simulator. That's a tool that can simulate a controlled disaster. For example, it can kill 3 out of 4 pods of one of your most critical worker services. Such action may have a failure chain that can help you get new findings about the way your system handles the disaster. This is actually a very good implementation of chaos engineering methodology. Instead of having many assumptions, there is nothing better than testing and monitoring. This is an infinity process that should be a regular ritual on your company if you have the resources. You have a steady state, you have a hypothesis, you run the experiment, you verify, you improve, and you run your experiment again. To summarize, let's go over the takeaways I would like you to remember. First, ROI, RTO, RPO, business needs, they should be your guidelines before tackling the technical part. You need to learn your infrastructure, know the limitations of your cloud provider services. As you saw, even if it's called a global service, it may not be fully functioning during a disaster, yeah? It's okay if your DRP is not perfect. Just be aware of the missing parts and what needs to be done manually. From now on, you need to have a DRP state of mind. On every move that the R&D makes, you need to think how it may break the DRP. New services, Terraform code change, deployment process change, etc. You need to create a detailed execution plan, document everything. Just imagine if your manual steps are complicated, remember they will be much complicated under fire when a new DevOps guy that is not familiar with the system needs to perform them. A DRP that is not being tested continuously means that you don't have a DRP. You can test it on a duplicated test DRP environment. It's kind of a chaos engineering that simulates a region outage. It can be done even on production, okay? I heard about a company where they prefer having production issues from time to time rather than having theoretical DRP that won't work when they really need it. That's a very inspiring approach. So that's all. You can find many references, resources, and examples in my page on 90 Days of DevOps. I'm available on LinkedIn and email if you have any questions, comments, suggestions, or anything else. You're welcome to read more of my tech experiences in my Medium blog. Thanks for listening. I hope you enjoyed. Bye-bye.